Hello everyone, Chapter 12, Section 12.4, Probability of Disjoint and Overlapping Events. So it's important to take a look at this first. It's an example. I don't label it as an example, but it is an example. If you pick one card from a deck of cards, can you get a king and an ace at the same time? From that one card, it's impossible for that one card to be both a king and an ace. So no, you cannot get a king and an ace at the same time picking one card. If you pick one card from a deck of cards, could you get a king and a spade? Yeah. There's one card in the deck of cards that is both a king and a spades, king of spades. So yes, you can get a card that is fitting both of these requirements, a king and a spade. So these two examples here show us the difference. They show us what mutually exclusive means. Okay, so let's take a look at example 1. We'll go through examples of mutually exclusive. Determine which events are mutually exclusive and which are not when a single die is rolled. Getting an odd number and getting an even number. Can you get an odd and an even at the same time? No, you cannot get an odd and an even at the same time. These events are mutually exclusive. So yes, they are mutually exclusive. Getting a 3 and getting an odd. Well, 3 is an odd number, so if you get a 3, it is an odd number. That is an overlapping event. Those are occurring at the same time. That is not mutually exclusive, so no. Getting an odd number and getting a number less than 4. Well, 3 is less than 4, 1 is less than 4. They are both odd numbers. So you can have both of these occurrences happen in the same time in one roll of the die. These are not mutually exclusive. No. Getting a number greater than 4 and getting a number that's less than 4. It's impossible to get a number that is both greater than 4 and less than 4 at the same time rolling a single die. So these are mutually exclusive. Yes. Example 2, we're continuing with the concept of what is mutually exclusive and what is not. This time we're going to roll 2 dice and we're going to get a sum of 7 or doubles. Well, the only way to get a 7 is to roll a 1 and a 6, a 6 and a 1, a 2 and a 5, a 5 and a 2, a 3 and a 4, or a 4 and a 3. None of those are doubles. The only way to get a 7 that would be doubles would be to roll a 3.5 and a 3.5. Well, 3.5 doesn't occur on die. They don't have 3.5 pips on the die, on the side of a die. So it is impossible to get a 7 or doubles in one roll of the 2 dice. So this is mutually exclusive. Select a student from your local college. A student is a sophomore and the student is a business major. Is it possible to be both a sophomore and a business major at the same time? Yes, it is. These are not mutually exclusive. Select any course. It is a calculus course and an English course. Is it possible to select a college course or even a high school course that is both a calculus course and an English course at the same time? No, that's impossible. That makes them mutually exclusive. There is no overlap. Select a registered voter. The voter is a Republican and the voter is a Democrat. Is that going to happen at the same time? It's impossible for the voter to be both a Republican and a Democrat at the same time. These are mutually exclusive. Select a student in your class. The student has blonde hair and the student has blue eyes. Is it possible for the student to have blonde hair and blue eyes at the same time? Sure. These are not mutually exclusive. No. Let's take a look at example 3. 2 6-sided dice are rolled. What's the probability that the sum of the numbers is a multiple of 4 or is a 5? Well, I want to take a look at right here the possible values. So we want multiples of 4 are 4, 8, 12, 16, 20, 24, 28, 32, 36. So which ones give me these values? So 1 and 3, 2 and 2, 3 and 1. Those are multiples of 4. Let's see, 8 would be 4 and 4. Here we go. 4 and 4, 3 and 5, 2 and 6, 5 and 3, 6 and 2. Multiples of 4 over here. Let's see. 12, 6 and 6. So, or is a 5. So we have 1, 2, 3, 4, 5, 6, 7, 8. There are 9 rolls that give you multiples of 5. So there are 9 rolls. Let me just clean up my paper here. 9 rolls that give us multiples of 5. And which ones are a 5? 4 and 1's a 5. 3 and 2's a 5. 2 and 3's a 5. 1 and 4 is a 5. It doesn't say multiples of 5. It just says or is a 5. So 1, 2, 3, 4 more. These are mutually exclusive. So we're going to add these together. We get 13 out of the 36 possibilities. Let's go back. Camera here. 13 out of the 36 possibilities is the probability. Okay. A bag contains cards numbered 1 through 20. One card is randomly selected. What is the probability that the number on the card is a multiple of 3 or a multiple of 4? So multiples of 3, 6, 9, 12, 15, 18. Multiples of 4, 8, 12, 16, 20. Now this is where we have to be careful because we don't want to count 12 twice. Okay, so one card is randomly selected. What's the probability that it's a multiple of 3 or a multiple of 4? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 20 possible cards, or 1/2. Okay, example 5 is tricky. And example 5, we're going to use what's on the front page here. It's called a Venn diagram. These Venn diagrams can be useful when figuring out some of these problems. So that's why I showed it to you. We've seen Venn diagrams before. I showed Venn diagrams to you back in, I believe it was chapter 2. Might have been chapter 3, but I think it was chapter 2. So example 5. Out of the 45 customers that ate at a breakfast cafe, 42 customers bought either coffee or orange juice. There were 30 customers who bought orange juice and 4 customers who bought coffee. What is the probability that a randomly selected customer bought both coffee and orange juice? So if we take a look at our Venn diagrams here, some of these people, 30 of them, bought orange juice. 40 of them bought coffee, but we have an overlap here. There aren't 70 people that bought coffee and orange juice. Only 42 of them bought coffee and orange juice. So obviously there's an overlap. And what's the overlap? Well, 70 minus 42 is 28. That's our overlap. 28 people bought coffee and orange juice. So that means that there's really only 2 people that bought just orange juice, and there's really only 12 people who bought just coffee. And of course, there are 3 people out here who didn't buy anything, coffee or orange juice. Okay, now back to the problem. What's the probability that a randomly selected customer bought both coffee and orange juice? 28 out of 45. Bought both coffee and orange juice. That's 62.2%. Okay. Medical Association estimates that 10.9% of people in the United States have a thyroid disorder. Suppose that a medical lab has developed a simple diagnostic test that is 96% accurate for people who have the disorder and 99% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. What's the probability that the diagnosis is correct? Now, I have a hint here. It says look at example 4 on page 696 in the textbook, and I've pulled that up here. Get that up on bigideasmath.com. So here's example 4, which is a similar type of a problem. American Diabetes Association estimates that 8.3% of the United States have diabetes. So, population in the United States starts our tree. 8.3% have diabetes. 91.7%, the remaining people, do not have diabetes. Okay, this is very similar to our problem. So we can start off our tree. 10.9% of the people have a thyroid disorder. That leaves 89.1% who do not have the thyroid disorder. Okay. Now, if we continue with the example, suppose a medical lab has developed a simple diagnostic test that is 98% accurate for people who have the disease and 95% accurate for people who do not. So 0.98 correct diagnosis, 0.02 incorrect diagnosis for the people that have diabetes, 0.95 correct diagnosis, 0.05 incorrect diagnosis for the people who do not have diabetes. So we have a very similar problem. So coming out of our people with thyroid, we have 0.96 is correct diagnosis, 0.04 incorrect diagnosis, 0.99 correct diagnosis, 0.01 incorrect diagnosis for the people who do not have the thyroid disorder. Okay, what is the probability that the diagnosis is correct? Now, if we go back, and so the same question is here: what's the probability that the diagnosis is correct? So now, probability that events A and B occur. Now they labeled A as the person has diabetes. B is a correct diagnosis. So for us, that's 10.9% and 0.96%. We multiply those together, so 0.109 times 0.96. And then we have to add to it, because these are mutually exclusive. You can't have diabetes and not have diabetes at the same time, or in our case, have the thyroid disorder and not have the thyroid disorder at the same time. They are mutually exclusive, so we add the two events that we're looking at. So A naught is the person does not have diabetes, and then correct diagnosis. So 0.917 times 0.95, and then they do the arithmetic. So we have 0.891 times 0.99. And when we do out the arithmetic here, we get 98.67% overall accuracy. Okay. Favorite ice cream. In a survey, 8% of the respondents said that their favorite ice cream flavor is cookies and cream. 6% like mint chocolate chip. These are mutually exclusive. You can't have two favorite ice creams. You can like them both, but one's your favorite and the other one's not your favorite. So because they're mutually exclusive, we can add them together. 0.08 plus 0.06 equals 0.14 or 14%. Either mint chocolate chip or cookies and cream as their favorite. Okay. Example 8. The corporate research and development centers in 3 local companies have the following number of employees. U.S. Steel has 110, Alcoa has 750, Bayer Materials Science has 250. If the research employee is selected at random, find the probability that the employee is employed by U.S. Steel or Alcoa. So 110 are employed by U.S. Steel, 750 are employed by Alcoa. The total, 110 plus 750 plus 250 is our denominator. When we do out the arithmetic here, we get 77.5% work for either U.S. Steel or Alcoa. All right. In a hospital unit, there are 8 nurses and 5 physicians. That's a total of 13 people. 7 physicians and 3 nurses are females. 7 nurses and 3 physicians are females. That's a total of 10 females. If the staff is selected, find the probability that the subject is a nurse or a male. Well, let's do the arithmetic here. There's 1 male nurse and there are 2 male physicians. That's a total of 3 males working on their staff in the particular hospital unit. So, find the probability this subject is a nurse or a male. So there are 8 nurses and 3 males. So 8 plus 3 minus, these are not mutually exclusive, minus the 1 male nurse out of the 13 possible people. So this is 10 out of 13, or approximately 76.9%. At a convention, there are 7 mathematics teachers, 5 computer science teachers, 3 statistics teachers, and 4 science teachers. If a teacher is selected, find the probability of getting a science teacher or a math teacher. So we have to create our chart. So we have math, computer science, stats, and science. We have 7, 5, 3, 4, for a total of 8, 11, 19 teachers altogether. Just want to make sure I didn't miss anybody. 12, 7, 19. Okay. If a teacher is selected, find the probability of getting a science or a math teacher. There are 4 science teachers, 7 math teachers. That's 11 out of the 19. teachers being selected, and that's 11 divided by 19, or approximately 57.9%, which I believe is wrong on the answer key. Okay, question number 11. Selecting a student. In a statistics class, there are 18 juniors and 10 seniors. 6 of the seniors are female, 12 of the juniors are males. If a student is selected at random, find the probability of selecting the following. So again, we need to make our chart. I did juniors and seniors across the top. And then I did male, female across the bottom. In the class there were 18 juniors, 10 seniors. 6 of the seniors are females. That leaves 4 of the seniors to be males. 12 of the juniors are males. That leaves 6 of the juniors to be females. This gives me 16, 12, 28 if I fill out the rest of my chart. A junior or a female. So there are 18 juniors plus 12 females minus the 6 juniors that are females, because this is not mutually exclusive. Divided by 28 is going to give me 22 out of 28, or 78.6%. Which again, I believe is incorrect on the answer key. Senior or a female. So there are 10 seniors, 12 females. 10 plus 12 minus the 6 seniors that are females out of the 28, which again gives us 16 out of 22, or 57.1%, which is correct on the answer key. Junior or senior, there are 18 juniors, 10 seniors, that's 28 people out of 28 people, or 100%. Alright, that was number 11. Number 12. According to the Bureau of the Census, the following statistics describe the number in thousands of young adults living at home or in the dormitory in the year 2004. So between the ages of 18 and 24, you can see the number 7922. And let's do our totals here. So if I total across the top, I have 10,456 males. There are 6,774 females, 13,701 between the ages of 18 and 24, 33,529 between the ages of 25 and 34, and a total of 17,230 young adults. Okay. Students. Choose one student at random. Find the probability that the student is a female student aged 25 to 34. So female students aged 25 to 34 is 995 out of the 17,230, and this is approximately 5.8%. Male or aged 18 to 24. So male, aged 18 to 24. So we have 10,456 plus 13,701 minus the males, so 7922 over our 17,230 altogether. And I do have percent, but let's do 10, 6 plus minus 922. That's 16,235 out of 17,230. Is 94.2%. That's the answer to part B. Part C, under the age, under 25 years of age and not a male. So under 25, not a male, makes them female. So 5,779 out of 17,230 is 33.5%. Okay. Example 13. In recent years, there were the following numbers in thousands of licensed drivers in the United States. So again, you can see the numbers. I've done the totals off to the side here. 9,263 are 19 and under. 3,178 are age 20. 3,306 are age 21. 8,050 are male. 7,697 are female. And our totals, 15,747 drivers. Okay. Find the probability that the driver is a male and 19 years or under. 4,746 out of the 15,747, or approximately 30.1%. Okay, so aged 20 or female. So age 20 is 3,178 plus female 7,697 minus the 1,553 that are both females and age 20 out of the 15,747. That's 9,322 out of the 15,747, or approximately 59.2%. Okay, at least 20 years old. That's 20 years or older. So that's 20, 21 years old. So these four. 1625 plus 1679 plus 1553 plus 1627 divided by the 15,747. 1625 plus 1679 plus 1553 plus 1627 is 6,484 out of the 15,747, approximately equal to 41.2%. Okay. If one card is drawn from an ordinary deck of cards, find the probability of getting the following. And these are the 52 ordinary cards in an ordinary deck of cards. I've got here for our visuals. What's the probability of getting an ace or a black card? There are 4 aces. There are 26 black cards, 13 clubs, 13 spades, plus 26 black cards, minus the 2 overlaps, the ace of clubs and the ace of spades. Out of the 52 cards altogether, that's 28 out of 52, or 7 out of 13, or approximately 53.8% chance of getting an ace or a black card. Probability of getting a king or a queen or a jack, that's the face cards. There are 12 face cards. They are mutually exclusive. We don't have to subtract anything. So we have 12 out of 52, or 3 out of 13, or approximately 23.1%. A club, heart, or spade. Clubs, hearts, spades. There are 13 clubs, there are 13 spades, there are 13 hearts. That is a total of 39 out of the 52 cards. Or we could have guessed, because that's 3 out of the 4 suits. So that's 3/4 of the deck, or 75%. Okay, getting a king, a queen, or a diamond. This is not mutually exclusive. So we have the kings and the queens are here. There are 8 of those. 8. There are 13 diamonds, plus the 13 diamonds, minus, because this is not mutually exclusive, queen of diamonds and the king of diamonds, so minus 2 out of the 52 cards. That's 19 out of 52, or approximately 36.5%. And that's the end of the section. Thank you very much.